Hey there, this is Seth Juarez from Channel 9. We're here in Studio F with Mehmet Uyen.
Egan.
Punched me in the face. So now that he's done some face compression, we're going to talk about Windows 10 memory compression.
That's right.
So why? Let's start with the why.
Why? So memory compression is necessary, in fact, beneficial, because overall we want to make sure that we can keep more data in memory rather than paging it out to disk and having to page it back in, right? Having to page it back in means when you're using your apps, right, then you're going to be faulting on disk, and if there are other IOs, those faults may take a long time, so you're going to get this unresponsive experience rather than keeping it in memory where we can immediately get it using just the CPU, right?
Everyone always asks me about memory, and I always try to explain it like, if you're drawing a lot of pictures and you have a bigger desk, you can keep more pictures on your desk.
Exactly.
But anytime you got a page fault, and it works because pages and drawing, you
Yeah.
have to go to the floor, pick up the page, and then to do that, you have to take a different page out, and so it just takes a lot of time.
Exactly.
So the bigger your desk, the better you are. But if you're constrained by the size of the desk, what do you do? And it looks like compression's the way to go.
Right. So then you essentially take these pieces of paper and you crumble them so they take up less space, so you can keep more of these crumbled things on your desk.
Nice.
And then if you want to work on one of those things, you just quickly uncrumble it, and that is much faster than kneeling down and like finding that page, getting that page, and putting it on your desk, right?
So it's just a way to make your desk bigger without having to make a physical desk bigger.
Exactly. And it also relies on this uncrumbling and crumbling being very fast using the CPUs, much more efficient than having to go to disk,
I see.
right, and then get that page out, because CPUs nowadays, we have many of them, and those are also extremely fast compared to the disks, right?
I see.
Another disadvantage of having to page stuff out to disk, like in our analogy, putting a page on your desk on the floor, is that the disks, their lifetime gets worse. When you write to them, they last for a shorter amount of time, right? So you want to reduce those writes, right? So the writes that are both expensive, they also degrade your disk over time. So this is good for better lifetime of your machine as well.
Especially if you're using the newer hard disks that aren't the spinning rust, but
That's
like
right,
the more you access memory from or data from them, the more they degrade.
Exactly. Like the smaller ones, for example, have a shorter lifetime. Essentially, the lifetime is determined by how much you write to them, right? So regardless of how expensive the SSD is, and there are some really cheap SSDs that are like used on phones that are really bad performance, but they also don't last a long time if you keep writing to them. So this eliminates that problem as well. So
I see. So not only is there a concern of speed, but there's also a concern of saving the floor from getting stepped on too many times, and it's going to break. That's good. Well, can we talk a little bit about how it used to be done so we can get a sense of how it's done now?
Sure. I want to mention like some things about like, there are like blog posts out there about this stuff, and I've seen like some questions about like, okay, what about battery life? What about like using too much CPU, right? So I will get into those things too, but like at this point I'm going to say, because disk also takes battery and power, right? Not writing stuff and not having to read stuff back in actually will save power. And for all of our measurements, we haven't actually seen much impact either way, because we compensate for that by using some CPU, right?
Got it. And
because all of the compression work that we do happens in the background at low CPU priority, it doesn't really impact any of the foreground work that you're doing.
I see.
Also, it's all workload based. So like if your workload doesn't require any of this, as in like you weren't gonna write anything to this anyway, anything to the disk anyway, we don't do anything. So in that case, it doesn't change. If you have tons of memory, you're not gonna see any compression, right?
Yeah.
Or if you have little memory and you're trying to do a lot of work, then you're going to see a bunch of compression. If you have a lot of memory and you're trying to do a lot of work, you're going to see a bunch of compression. Again, all to reduce how much we go to disk and make everything faster by keeping it in RAM.
I think developers often forget, I know I do, that I/O stuff takes orders of magnitude more CPU cycles than to get stuff from RAM, for example, or even the cache that's on the CPUs.
That's correct.
All right. Well, let's take a look. Maybe you can draw some stuff for us.
I will. So I will talk about some of the history of this, right? So this is actually not something that we just did in Windows 7. This was something we were working on since all the way back in Windows 7. Oh, I missed. So
yeah.
It's not something we just did in Windows 10. It was something we were working on since Windows 7.
Got it.
And during Windows 7, the environment was different. So it was it was more scaled back than what it is now. At that time, we were using completely non-page memory for this compressed data. There was integration with the disk I/O stack as well as the memory manager, right? And this was primarily geared towards the Ready Boost feature that we had. Like this feature, if you remember, like where you could put in a USB key and then use that as cache. So that cache, so this cache is now backed by that USB key space, right? And we were compressing it in there, okay? And over the years, our focus changed based on like what the customers needed and what the hardware needs were towards more like in-memory compression. So that's Windows 7. And then Windows 8.1, we did more work around, well, okay, let's actually do this thing compressing memory onto memory, right? So in Windows 8.1, we actually enabled this thing everywhere. And it was less visible, but it was less scaled out compared to Windows 10. We were only using it in cases where it was a cache at the time. So the pages would get written out to the page file, they would get paged out, and then we would compress them. So we would have a copy of the page in compressed memory. And then that was also just a cache. So it could have been thrown away, it could be reallocated by other applications. That was a different approach, but very related in our work towards like where we are now. In Windows 8.1 Spring 14 release, we actually changed things around dramatically where we said, you know what, we don't want this to be a cache. We want to actually prevent pages from getting written out to the page file at all in the first place, right? So now this becomes not a copy of the pages, but it becomes like a compressed page file that is kept in RAM, okay? Which is really what this thing is, right? It's a compressed page file in RAM, right? Which itself can be paged out to the real on-disk page file, right?
So in 8.1, you were essentially compressing it and then paging it out. And it was a lot faster. It's a lot faster to get compressed page memory back in because it's smaller.
Yes.
But now you're saying we went to the next level in Windows 10 and we're going to keep the crumpled up stuff in RAM.
We were trying to keep the crumpled stuff in RAM as well, but we were applying this compression thing to a subset of data on the machine. We were applying it only towards low memory machines, those machines like the little tablets that are like with 1 gig of RAM. And we were only applying it to the Windows 8 modern apps, right? With Windows 10, we are applying it everywhere. In fact, with Windows 10, anything that you find in your real page file is already compressed. There's nothing uncompressed in your page file anymore. So in Windows 10, and I'll explain how this works in more detail, we will compress the pages, right? Prevent them from getting written out at that point. We'll keep them in RAM as long as we can, right? But if machine resources dictate, like we are low on memory, the memory manager will still take our compressed pages and write them out to the page file. So with that, there's really no limits on how much we can compress because it's all pageable memory, right? And eventually it's going to disk. So, but then compared to before, we're writing a lot less data to disk. And in many cases, we don't have to write to disk at all because once we compress them, we don't have memory pressure anymore. So there's no more read to write.
I see.
You see what I'm saying? That's why it's a good thing that kind of just makes the whole experience better.
Cool. So we're using a lot of terms that maybe developers haven't heard yet, like paging, page file. There's also this term called working set. Is that
I will explain all
what does that all mean? Maybe we can look at some diagram that you can draw.
Sure. So the way things work, so I'm going to now use the board like to explain like how things work before memory compression. Okay. So the way Windows memory management works is applications, they run and then they access what we call pages. Pages are essentially, simplifying, it's a 4 kilobytes of memory block. So memory manager manages memory in 4 kilobyte chunks. Okay. So when you allocate memory from your heap and you start accessing it, that creates a page fault and then memory manager allocates a 4K page and gives it to you. That page goes into your working set. So for each app, there is a working set, right? And then there are like pages in here that you can access. All right. What happens is over time, as memory demands on the machine become higher and the machine feels like it's running out of memory, the memory manager will say, okay, maybe there are some unused pages here that I want to take out. so that I can reuse those pages for other people's allocation requests.
And it knows because it just hasn't been accessed.
It hasn't been accessed. Memory Manager knows this because it looks at this stuff periodically.
Got it.
Okay. So now when that operation is called a trim, right? So we will trim pages from the working set. So now the working set contains both what are called private pages and file pages. Like file pages are like your DLLs that you are mapping that are using into your address space, right? And then there are the private pages, which are pages that you allocated. Like your heap, your virtual alloc, like those kind of things are private pages, right? So most of this stuff is about those private pages. Private pages and page file backed pages. You can also allocate shareable pages that are backed by the page file that you can share with a different process. So those are all candidates for compression.
And when you say page file, that's the file that's copying the memory, that's the file on disk that has the memory?
Exactly. That will have the memory when we page it out. So I'll explain how that works. So let's say we trimmed a private page. Okay. If the page, so those pages when they're trimmed, they will go to what's called the modified list. Okay. So dirty pages go to the modified, as in like this page has data in it that hasn't been saved anywhere, therefore it's modified. So it goes to the modified list.
And it's just not being used right now.
It's not being used right now. That's why we trimmed it.
Okay.
Right? And then, pages can live on the modified list for a long time. It will just get trimmed, and then they can stay there for a long time. That way we can generate bigger writes, right? After a while, or soon, depending on what the memory management policies do, they will get written out to the page file, right? Page file is obviously a file on disk. Okay. So
and that's a literal file. I think it's pagefile.sys. You'll find that.
It's a pagefile.sys that lives in the root of your C drive, or you can create more page files if you want to. Now, the write doesn't have to happen. Like while it's on the modified list, if the app decides to use that page, we'll just take it out of the modified list and give it to the app. No write necessary. So if they stayed on the modified list for some time and the memory manager was like, okay, let me write these things out, it will write them out here. And then, after writing them out, the page still has the data. We don't throw away the data because why would we, right? We will take that page and we'll put it on what's called a standby list.
I see. So it's actually still in memory in the standby.
It's cache now, right? So this is what you would call the page cache on the machine, right? So along with what's called the free list, free plus zero list, right? These two things are called available memory. Okay? It's called available memory because if another application wants to allocate a page now, the memory manager will say, oh, if I have 3 or 0 pages, I'll just take it from there. If I don't, then I'll go to the standby list and I'll take the least recently used page there, right? Okay. In practice, it's a little more complicated because we have prioritization here as well, which I'm not going to get into. But effectively, you take the least recently used page from here and you add it to your working set, okay? And that operation is called repurposing.
So I've heard the term page fault before. Is that the same as repurposing or something different?
So when you take a page fault, right, it can result in various different operations. When you take a page fault, the page that you're faulting on might be in memory. It could be on the modified list. It could be on the standby list being cached already, in which case it's a soft fault. You just take that page from there, you put it in your working set. That's a very quick fault. That's what you want, right? Or that page may not be in memory.
Because it's been repurposed.
It's gone. It's been repurposed in the past. So you have to allocate a new page, and go read it in from disk from wherever it was, right? In that case, you either take a page from the free or zero list, or you repurpose a page from the standby list, and now you have a page, right?
And that's a hard page fault.
So there are two cases there too. Either it's a hard page fault because it was repurposed before and got written to a page file, or it was already coming from a file before, or it's a brand new page that we've never touched before.
I see.
So in which case, we just zero it if it wasn't zeroed already, and then we give it to the app.
Got it.
Okay, so that's what we call a demand zero fault.
Okay.
So as a result, taking a page from standby and coming into the working set may either be just a soft fault, or it could be a repurpose, as in like I repurposed that page, right? Okay. Like I said, similarly, modified pages can be soft faulted into the working set as well. So let me go through the lifetime of a typical page, right? Let's say I ran the Edge browser, right? You go into some web pages, and then you've opened another tab, and you haven't been using a tab for a long time, right? Over time, what's going to happen is those pages aren't being used, right? These things use a lot of memory, therefore soon the machine is like, oh, let me go trim some pages because I don't have enough available memory, right? We try to keep like a healthy amount of available memory on the machine so for people can make allocations efficiently, right? So the memory manager will go, okay, let me trim some pages from this Edge process. The page will go to the modified list, right? It will sit there for however long it sits there. It could sit there for many minutes, an hour, hours. If you, at this point, switch back to that Edge tab, you will likely get soft faulted back in. If you don't, and it sits there for a while, memory manager will say, okay, let me write this to the page file. It will write it to the page file. That page will go now on the standby list. Now, while it's on the standby list, it's still resident, right? So if Edge were to access it, it would soft fault it directly in with no cost, right? We just did this right, which is not great, right? But at least the fault was fast, right? But the problem is, standby list, it will churn out very quickly. For example, if you were copying a file, you download a big file, right? You play some big game, it's very easy, even on machines with a lot of memory, to churn through this thing, to repurpose everything that is on the standby list, right? Over time, that's what's going to happen. As allocation requests are coming in, as apps are accessing files and other things, they will take pages from here. So whatever is cached here, soon, right, will be repurposed, right? Therefore, when you switch back to that Edge processes tab, you will take a bunch of hard faults now.
Straight to the disk.
Straight to the disk, because we're going to be like, oh, that page is not resident. We will repurpose another page from standby, and we'll go, where's this page? This page is in the page file. We'll go read from the page file, and then add it to the working set.
And that's when your hard drive starts blinking a lot, and then things slow down. Yeah.
Exactly, and that happens when you switch back to something for any app. When you want to close something, it might fault. So it is really the root cause of most performance problems on client and server machines, unfortunately. Especially on rotational disks, where these reads are extremely slow. But even on SSDs, they're much slower compared to what the CPUs can do.
Of course.
Right? So now let's talk about what compression brings into this picture, how it changes this picture, right? Well, it really doesn't change it that much when you think about it. Compression will come in at this point. Okay. We have already, we did everything. So we have this modified list. Again, we don't really change how much stuff is on the modified, how long it stays there. But at this point, the memory manager decided that it wants to write to disk. We come in at that point and we say, oh, we're kind of like a page file. So why don't you, whatever you were going to write to the page file, instead write it into the compression store.
I see.
Right? So now that is where we come in. Essentially, this page, instead of getting written to the page file, ends up getting sent to what we call the store.
Now, is the store in memory?
So let me explain what the store is, right? So first of all, we don't have one store, we have multiple stores. What we do is, a store is essentially a collection of pages. You can add pages to the store, in which case the store will take it, it will compress it, and it is kept in the system process working set.
Oh, I see. So the system process is the actual OS.
Yes. And this is kept, the backing memory for the store is allocated from the user mode address space of the system process.
Oh, I see.
Which, over the last 25 years of Windows, was not really used very much at all. It was largely empty, right? It was maybe some drivers could use it, but like it was largely empty. And that's why normally when you look at it in Task Manager, you see like, oh, it's like using 8 kilobytes or like 20 kilobytes or whatever. And now, because we keep the store, actually multiple stores there, it can be gigabytes. There's no limit. But it's essentially acting as a compressed page file.
Well, not only that, but the store, since it's in memory, it's not having to write to the disk, which is going to make things faster when the modified list writes to the page file, which it's not doing anymore.
It's not doing, essentially, it's writing to this compressed page file, right? And again, the compressed page file itself, this memory backed by the system process, is itself pageable.
Right.
So if we have too much stuff here, memory manager will go, oh, let me trim that. I'll trim that and put that on the modified list.
But whenever you're trimming from the system, you're not recursively going to write to yourself.
No, at this point we're going to be, some of these are system pages.
Got to write.
They're already compressed. Those go to the page file.
Got
so
it.
essentially, you get a second lease on life, right? Instead of directly going to the page file, you know what? Let's go compress it into the store, and let's see what happens when you compress into the store. We'll compress into the store. That will make these pages take less space. In fact, they take like the result of the compression. If it's like a megabyte thing, it kind of turns out to be like 300 to 400 kilobytes. So they get down to 30 to 40% of their size.
So you're using less pages in essence for the pages that otherwise were a lot larger when they were in the working set of a process.
And the pages that we freed up, let's say we're compressing a megabyte, right? We'll compress that megabyte in here, and then those pages that were freed up, because now we compressed a megabyte into 300 kilobytes. The remaining 700 kilobytes will go to the free list.
Which is the best list to be in.
Which is the best because it's the cheapest thing.
Yeah.
Right? So those are the remains of the compressed data, right?
That's cool.
So that's why this is very nicely integrated with the memory management hierarchy, where there are no limits. This is not non-paged memory, right? There is no limit on how much it can grow, right? And it itself is pageable. Therefore, all the memory management policies that we have around choosing when to trim apply to that guy too.
I see.
And therefore, if there's a reason, so what we expect to happen on most machines is that, like, today people have machines with like 4 gigs, 8 gigs, 16 gigs of RAM, right? Previously, the result of a trim would be a pretty much deterministic write to the page file and a subsequent read because it would get repurposed off the standby list. Now, for most customers, I would say running Windows 10, through this compression, we can keep everything they're doing in memory. So I would say the amount of paging people will experience with Windows 10 is going to be an order of magnitude less compared to other OSs we've shipped, because we are that much aggressive about relying on compression to keep things in memory.
And so if you're looking at the system and you're complaining, wow, the system is using a lot of memory, that's actually a win because that memory otherwise would have been expanded and pushed out onto disk, which was going to cause a lot of thrashing if you're opening tons of huge applications.
Exactly, right? So in fact, when I look at my task manager and I see a lot of 7 system process, I'm like,
because it's in RAM, because otherwise you're going to disk. And,
and again, if it needs to go to disk, it will still go to disk, right? If there's like so much pressure that we need to page that out, that's fine. But then, as a result, we have written like 70% less data to disk as a result, even if we were writing. But in many cases, because compression will increase available memory, we will not have to write in the first place, right? Even though we would have before, right? So for a lot of people, I expect them to experience, I used to go to the page file, like I used to see a lot of page file I/O, right? You will not see anything anymore for many cases, right?
That's pretty amazing. And the thing about it is that's amazing is that most people won't even realize this is happening. They'll just feel things, they'll be a little snappier.
Yes.
There won't be this like hang when things are trying to load up from
And I'm not talking about just machines that have like SSDs on them. This is like people, especially people running on rotational machines, right? People running with a lot of memory, right? In the past, pages would get paged out from those things. Now, we have adjusted our memory management policies that we are saying, you know what? I'm not going to take these pages out, right? Except like file pages I will not take out. Private pages I will take out and then put them in here. But this one, right, I will try to keep them as long as I can in the system process because it's resident. I don't want to write them to the page file.
Right.
And because that might mean a subsequent read, right?
Awesome. So if you open your task manager and you're starting to see your system process take a lot of RAM, you should be excited about that.
And also, keep in mind, what this means is if you have enough memory such that nothing was going to get trimmed from your working sets or nothing was going to get written to the page file, nothing is going to get compressed either, right? So it's not like this is like a tax, right? If you have enough memory, you will not experience any compression, right? Or if you don't do much with your machine. But if you do, and we would have written to the page file, now we're going to come in and compress those pages to avoid that page file write.
So let's talk a little bit about, because obviously this isn't free. Even though we are freeing up a lot of cycles by avoiding I/O reads and writes, there's still going to be some tax on the actual compression. Can you talk about that a little bit?
Yeah, so that's an interesting point. So obviously, in order to compress these pages, right, we have to use CPU. Mm-hmm. And similarly, on the way back, like if somebody faults on a page that we have put in the compressed store, we have to decompress that page, right? Now, let's talk about, so what my assertion is that, and based on the data that we have, compared to the disk read and write rates, the speed with which the CPU can compress and decompress these things, it's much faster. So let me give you some numbers, for example, right? So the way this works is, first of all, compression is just like page file writing, is a background operation. So whatever CPU it uses, it happens at low CPU priority. So it will never interfere with something else that you're doing, right?
Like a movie, for example.
Like a movie, like you're browsing, you're playing a game, like all those things, this is happening at low CPU priority. So if there's something else that is happening, the CPU scheduler will run your stuff rather than this stuff, because this stuff is not urgent.
Sure.
It only becomes urgent if you are literally running out of memory.
Yeah, that's right.
So we're like, oh, I need to compress these pages, then it's going to run at higher priority, right? But that's going to be extremely rare for many cases. So that's one thing, right? The other thing is the compression rates that we see on these machines today are actually very very high. Like on my, I don't know, 3-year-old desktop machine, I get about like 300 megabytes per second compression per core.
Wow.
Right? So we do compress on multiple cores when we have multiple stores. So you can do the extrapolation from there.
Yeah, with a 4K page file, that's a lot of pages you can compress.
You can compress a lot of pages, right? So on the other hand, what is even more amazing, I think, is that what really matters more is decompression, because decompression is when people actually are doing something. Like you switch back to that Edge tab, and now how fast we get the pages. How fast we decompress those pages is going to determine how fast you see that edge, right? And again, compared to reading it from disk, or even like compared to a soft vault, we're extremely fast, because in my machine's example, we can decompress at a gigabyte per second per core, right?
Wow.
So, and this scales very well, right? So this scales extremely well because it's entirely a parallel thing. And on my machine, I was actually get 7.7 gigabytes per second across all my 8 cores, right? So, again, this works similarly, even on a much cheaper, like a Bay Trail machine, right? Like these like small tablets, we can get about 600 megabytes per second per core. And Bay Trail has 4 cores, right? So, and compared to even the fastest SSDs that people might have, this is just far faster, right? Even on the lowest end phone that like the Lumia 520s, 530s, right? Even on those things have 4 processors. And across those things, we can decompress at about 250 to 300 megabytes per second, which is way faster than like how much reading that this can do, or writing for that matter, right?
So essentially, this is a calculated trade-off. We want to avoid the I/O cycles, which are orders of magnitude more than decompressing and compressing.
Right, and at the same time, the CPU work that is done for compression is low priority. It's not going to interfere with anything, right? Because it's avoiding the disk write, which saves power, right? Which saves disk lifetime, right? Overall, from a power perspective, we don't see this impacting anything at all, right? There is no negative impact according to our tests. But then that makes sense because we're using a little more CPU, but we're saving a bunch of disk writes and reads. So it ends up being a close call.
That's actually an interesting point you made, because I just realized that Windows 10 works across a variety of, like if you're working on your Raspberry Pi, you don't want to be reading and writing your page file to the SD card.
Yes. So this is a very targeted thing that we enable per SKU, right? So right now we're enabling on all the desktop SKUs. So you're running a desktop or a laptop or those kind of like a tablet, those things have memory compression enabled by default. And on Windows Mobile, right, we also have like all the phones that are running Windows 10 also have compression enabled by default, because it's really good for those guys.
Sure.
Because those guys don't have a lot of memory and their disk is much slower compared to the other guys. So one other thing I wanted to mention here is like this concept of a store, right? So we actually have multiple stores. The way this works is stores are associated with processes or groups of processes. So the way we do this is at boot time, we create a store for the system. Okay, so this is, let's say, it's called as the system store.
And so that's just anything that's used on the system.
So if you don't have a store for your process, this is where you go.
Okay.
Okay? And for some processes, we say, I want to create a store for you because you're special, right? The special processes are all these, the modern Windows 10 applications, right? So the modern applications, since we've had since Windows 8, including the universal apps and including Windows 8 and 8.1 apps, right? So those guys get their own stores. Why? Right? So those things are different. So those guys they're modern applications, so they have a modern application lifetime. And we take advantage of that lifetime to make the switches to those applications and their memory management very efficient.
I see, because those things, when they're swapped out, they're almost swapped out entirely. Like if you're working on a phone app, once you swap it out, you're not going to be looking at it at all.
That's correct, right? So when you switch away, right, from these apps, either in Windows, like where you minimize them, on desktop Windows, or in phone, where you switch away from them, those applications are suspended, okay? They will not run anymore. Now, that gives us a lot of power to optimize things, because then what we can do is, nobody's going to be using this app for at least a few seconds, right? So on a low memory device, we can be aggressive and say, you know what, I need to get this out of memory right away because there's so little memory. Like, this is a 512 megabyte phone, right? That's like so tight, right? So in such cases, or a 1 gigabyte tablet or something, right? In those cases, we are very aggressive. We go, boom, I'm going to now empty your working set, your private working set. And this is like trim every single private page, page file pack. Those pages then go boom, and then we force them out to their store.
Got it.
Right? So let's say you're using the Maps application, right? As soon as you switch away, application gets suspended. We're going to go empty its private working set and then push the pages into the store. Okay? So they will be all boom compressed right away, and all of a sudden, 70% of whatever memory it was using, boom, will become free.
That's
right?
amazing.
That is very important, because now, presumably, you're switching to some other app which needs a lot of memory. Right. So there it is, right?
There's a lot of free and zeroed memory.
So it's really like relies on performance on this. It relies on this life cycle, right? Where apps got suspended, they get compressed. Compression yields a lot of free pages, which are then used for the other app, right? So having this be really fast is important. Otherwise, if you were to write those, let's say it's a 100 megabyte app, right? If we were to write those 100 megabytes to disk, even if it is sequential on these low-end phones, it's going to take forever. Those things write up at like 7, 8, megabytes per second, and that will take forever to generate enough memory for the next application.
I see. Well, can you talk a little bit about, because obviously the working set is virtual memory versus physical memory. The virtual memory might be in sequence, but it might not be in sequence in physical memory. Do you do anything with that when you write out to the store?
So that is interesting. So in Windows 8, we came up with this optimization for these modern apps where we have this concept of swap, which is kind of similar to this, right? If we didn't have compression here, right, swap essentially says, you know what, I'm going to empty the working set. We also reserve sequential space in the page file for this application's pages. Like application 100 megabytes, we reserve 100 megabytes or something close to that, right? And then when we write them out, the writes are all sequential, which is of course much more efficient than otherwise. It would have been otherwise, especially when it's time to switch back to the app where we need to now in-swap, right? Yeah. So now we can do the in-swap using sequential IOs, whereas normally those IOs will come all over the page file, and even on SSDs or on rotational disk especially, that will be much slower than doing large sequential reads where you can get a lot better throughput, right? Now with compression, we want to maintain that, right? But now we know that I don't have to reserve 100 megabytes on disk for this app because I know I'm going to be compressing it. So what we do is, because this is an application, it has its own store, right? So we put the pages in the store, all back to back virtually, right? And then we reserve space in the page file for the store. Now let's say 100 megabytes compressed to like 40 megabytes, all back to back. We reserve sequential space for it in the page file, and we swap out the store instead of swapping out the app, right? So now when you switch back to the app, we're going to be, I need to now, bring all the app's pages back in. We will do this prefetch operation, this in-swap operation, which will go and say, all these pages are in the store. So now on all cores on the machine in parallel, we're gonna be doing reads on this stuff, and in parallel to that, we're gonna be decompressing all these pages. Okay, so it's an extremely efficient mechanism, especially when they're compressed, to get them back into memory, right? And in that, because we parallelize the disk reads for the 40 megabytes with the decompression of that 40 into 100, we actually essentially get like just we can get about like the full decompression performance. Decompression ends up being the long pole because the reads are compressed and they're smaller, right?
I see.
So we just get it back, and that's why switches are so fast. If we even had to page it out, of course,
I see.
Right?
So you talked a little bit about parallelizing the decompression. How is that happening? Since the memory is all sequential, how do you decompress all this? Is it easily?
Let me explain. Right. So in these prefetch operations, where we are going to be bringing large amount of memory into the application, this in-swap operations, this working set in-swap operations. Essentially, the way that works is we have recorded the contents of the working set before the app suspended. Mm-hmm. And now the app is about to resume. So now we're going to say, oh, all of these things that used to be in the working set, now I need to bring them back in. Okay? So we have a big list. So what we do is we say, okay, I need to parallelize this prefetch across all the processors that I have, right? So all of those processors, we say, okay, you take this virtual address, you take that virtual address, you take this virtual address. So everyone goes and faults it from the store.
I see.
And because essentially when you are faulting from the store, everybody does it on their own thread. There is no like serialization, right? So in parallel, all cores are getting their own pages from the store. And when they do, the store itself now might be paged out, swapped out in this case, right? Mm-hmm. That's why we first initiate an in-swap of the store pages.
I see.
From this, so those are coming. So that's why as soon as they come in, they get decompressed. And while they're getting decompressed, the next page is that the next megabyte is coming in. So that's why this operation essentially, the disk read completing and the decompression threads happen in parallel, so it's much faster than it would be if it were serialized, right?
That's awesome. So again, if you're looking at your system process and you're seeing there's a lot of memory in there, just remember that memory's been compressed.
That's correct.
And it means that you're not going to be faulting to I/O or disk.
And in practice, like I said, for most customers of Windows 10, I would expect that all of these things, once they get compressed into the system process, we will not need to trim it from that. So you will not, like this in-swap of the store is largely not going to be necessary for many customers, right? It's only necessary, we experience it in these low memory machines where these things are prone to, there's so much memory pressure that even the compressed data needs to get written out. And we try to do that in an efficient way, right?
All right. Well, this is pretty awesome. I'm going to come step back in and say, thanks so much for spending some time with us. This was really awesome, learning about how you're doing memory compression in Windows 10.
Sure.
Thanks so much, bud. Hopefully we'll talk to you more about new stuff.
Thank you very much.
Thanks for watching, and we will see you next time. Take care.